Hi everyone, this lesson is on graphical relationships, and we'll be talking about the basics of those relationships and what you need for this course. When we look at a graph, we want to be able to look at the variables that are there and look at the relationship between those variables to draw conclusions. So there's times where we'll be looking at the slope of the line, and there are also times where we'll be looking at the area that's under the line. And both of those things tell us more about the relationship between the variables involved. We'll be talking about three ideas. We're going to be talking about types of graphical relationships, how to make a graph, and how to find slope. The first type of graphical relationship we'll look at is a direct proportion. And I just want to show you what that looks like to begin with. We can see that if this is our x-axis, as the values increase on the x-axis, and we can see that the values on the y-axis also increase. So if that's true, and both variables as they increase, the other also does the same, increases, then we have what's called a direct proportion. How that looks in the equation is like this: y equals some constant times x. So if we were to insert some sort of any number for x and increase that number for x, we should see the y values also increase at a constant rate. And that's what we have here. We talk about constant rate, we're looking at the slope of this line. The slope of this line is not changing. For instance, it's not curving up, it's not curving down, okay? Or however, there's no curve or change in the slope or steepness of that line. It's remaining the same throughout. So we have a constant relationship there between the variables, and this is a direct proportion. The second type of relationship is called a direct square. Again, I'm going to show you what that looks like. The direct square has a curve up. It's an exponential increase in the values. Again, we'll talk about the x and y axis. As the x-axis increases, these numbers must increase here. As this x-axis increases, we see that the y values increase, but they increase at an exponential rate. So they increase, more, all the way up to infinity. So this is a direct square. Example of this in equation form is y equals some constant times x squared. So if we were to plug values in for x, as this value increases at a steady rate, y will increase at an exponential rate because this value is squared. The next is called an indirect relationship. Indirect relationship is also called an inverse relationship. Now, this one is a little tricky. People do get confused by this. What I've shown you here is an indirect relationship. As the values for x increase, the values for y decrease. These values go down as we go along the positive x-axis. How this looks in an equation is y equals some constant over x. So I like to talk to my students about upstairs and downstairs, meaning numerator and denominator. So y is in the numerator. It's above or upstairs, the 1. C is a constant, we don't really need to worry about it. X is our other variable, and it's in the denominator, it's downstairs. So very quickly we're able to see that as one variable increases, say x increases, then we know that this value becomes, say, 1 over 2, 1 over 3, 1 over 4. And if we graph that, we have, 1/2, then 1/3, then 1/4. our graph ends up having this small curve in its line. Okay? Some people do confuse this with a graph that looks like this. This graph has a negative slope. We still have an indirect relationship because as the x-axis increases, the y-axis also decreases. So the only difference is that this graph has a negative constant slope. And it could just be that we're looking at a very small area of our graph up here. If we were to zoom in on this small area, we would see a pretty linear relationship from one point to the other on the graph. And it may end up looking like this graph here. The last relationship that we really need to know for Regents physics is the indirect square. The indirect square looks like this. We can see that as x increases, y decreases at an exponential rate. The equation looks like this. Y equals some constant over x squared. So as this value here, x, increases, 1, 2, 3, it becomes squared. And then we have 1 over the square of x. And y decreases exponentially due to this squared x. Typically, when you see an exponent in an equation, you will end up with a curve in the line on your graph. Now we'll take a look at some equations from our physics reference table. And it doesn't matter that you don't know what these terms mean yet. All we're looking at is the relationships between variables within those equations. So the first one we'll start with is the F equals m times a. F equals m times a, I'm looking at the relationship between F and a. So let me set up some axes. And I'm going to place a on this axis and F on this axis. Now as a increases, what happens to F? If we put numbers in for a, what happens to the variable F? It also increases. So we know what that looks like. That is a direct proportion. There's nothing squared, and they are both upstairs, meaning that they're both in the numerator, F and A. They have a direct relationship between them. Now let's take a look at the next one. We'll look at R equals V over I. Again, it's not important what R, V, and I are. So let's look at the relationship between R and I. So I'll place I here on the x-axis and R on the y-axis. Now, if we were to put numbers in for I, and those numbers increase, what happens to the value of R? Well, R decreases. So as I increases, R decreases, and now we have an inverse relationship. Okay. Let's try the next one. So let's look at the equation KE equals 1/2 mv squared. So for this graph, I'm going to look at the relationship between speed, which is V, and KE, which is kinetic energy. Now, as speed increases, and we square that speed, what happens to the kinetic energy? Well, if we put 2 in here, we have 2 squared is 4, so we have 4 times the kinetic energy. If we put a 3 in here, it's 3 squared, we have 9 times the kinetic energy. So we see that the rate of increase is exponential. So what does that look like? Again, we've talked about that relationship. That would be a direct square. As V increases, KE increases exponentially. For the last one, we'll use F equals GM1 M2 over R squared. And we will look at the relationship between F and R. Now F is in the numerator, it's upstairs, and R is downstairs in the denominator. So as R increases and this value gets bigger, what will happen to F? Well, F will decrease, and it'll decrease at an exponential rate because we are squaring R. So this would become 1 over 4 and 1 over 9 and 1 over 16 and so on. So what does that look like? That is an exponential decrease in the value of F as R increases. Next, I'd like to talk to you about how to make a graph. I know that most of you know how to do this, but I just want to go over some pointers. So let's say that we have a table of time and distance. Notice that in the table headings, we have the units, seconds for time, and meters for distance. And this was the given information here. So I've made a rough graph. I'm just going to do a sketch. And one of the things that you want to do is make sure that you're labeling on your graphs the axes. So in this case, I'm going to place time on the x-axis, and you also want to include units in those titles. And we'll place distance on the y-axis, and again use units. Sorry for my messy handwriting. Next, you want to look at the data that's given and determine the scale that's necessary for your axes. So on the x-axis, looking at time, we're ranging from 0 to 5 seconds. So I can just simply go by 1 second for each hash mark here. So we have 1 second, 2 seconds, 3, 4, and 5. You want to use as much available graph space as possible. On my distance information, I have 0 to 100 meters, and so I want to spread that out as far as I can. So I have 1, 2, 3, 4, 5, 6, 7 spots. I can divide 100 by 5 and use 5 spots out of those 7. Again, you don't want to make yourself crazy. Use things that are easy to plot. So we'll go by 20s here. 20, 40, 60, 80, 100. Okay, so now we're ready to plot some points. So we have 0, 0. We have 1, 18. We have 2 and 40. We have 3 and 62. We have 4 and 80. And we have 5 and 100. And this is just, a rough sketch here because I don't have graph paper. So then, once your points are plotted, you want to create what's called a best fit line. I would say 95% of the time, we do not connect the dots. We use trend lines or best fit lines, as you've heard before in other courses. So using a straight edge, we're going to create a best fit line. So for this best fit line is an average of your data. So you don't want to be too far above your data, and you don't want to be below your data. You want to have equal number of points above and below your best fit line, showing the average. You don't have to start it at 0, 0 unless 0, 0 is part of your data set. A lot of people think that they have to start a best fit line at the origin, and that's not true. In fact, some best fit lines would have what's called a y-intercept. Not for our data here, but right here would be the y-intercept. It's where our line intercepts the y-axis. So just be aware that you don't necessarily have to have your best fit line go through the origin unless your data set includes 0, 0. So the next thing we would want to know from our best fit line is the slope. The slope formula is change in y over change in x, and this delta here means change. So we want to show the change, or how the y-axis is changing, 1 point minus a second point, or difference. And again, on the x-axis, the change on the x-axis between 1 point and another point. So when you determine slope, it's imperative that you use 2 different data points and 4 values. You cannot use just 1 point on your x-axis and 1 point on your y-axis, because that does not indicate slope. Slope is the slope of a line, or steepness of a line. Can you find the steepness of a point? So no. So that's why we need 2 points to create the slope. So now if I have some data points here, say they're here, and I create my best fit line, and we'll make that in blue. Okay. Now I want to pick 2 points on my best fit line, and what I like to do is create a triangle. So I see that this point up top and this point down here fall on my best fit line. So what I'm going to do is I'm going to create a triangle, a right triangle, and what that allows me to do is to look at where that point falls on the x-axis and where it begins here on the x-axis. So this would be called x1 because it comes first, and x2. I can also see where those points fall on the y-axis. So this would be y1 and this would be y2. So now I can look at my axis and clearly have those values and use them to calculate the slope. So when we set up our equation, we want to set it up as the change in y over change in x. You've picked 2 points on your best fit line, and we can very easily make that calculation. Just one other thing to mention. So at some point in your career, your school career, you might have heard the term rise over run. So I'm going to explain what that means. So the rise is how far the line rises in a given period. And so this is your change in y. Change in y is the same as rise. And how much did it rise for a given run or change in x? And this here is your run. And your run is the same as change in x. So when you hear rise over run, we're really talking about change in y over change in x, and it's the same thing as slope. Okay, hopefully that helped.
Yeah, it was devastating. It was.
Not only is slope a useful tool for determining relationships between variables, we can also look at the area underneath of a line. So let's say that this is our trend line. The area underneath the line can tell us also about other variables. So the formula for area of a rectangle is base times height. The area for a triangle is 1/2 base times height. And the shape that we're looking at here is a triangle. To understand what variable the area is representing, we have to look at what's on our y and x axis. So the base here, the base of our triangle, is along the x axis. So I'm going to substitute in x for the base, or change in x for the base rather. And the height is going to be change in y. So if we have a formula where two variables are multiplied by one another, say it is v times t, I would look on my reference tables and know that v times t is equal to d. So if v were on my x-axis and t were on my y-axis, then I know that the area underneath that line is representing distance. So we will practice this quite a bit, and you'll see how to use this and develop the skill of looking at the area, and how it can be utilized to tell you more information about the relationship between those variables. Okay, so it's time to practice our graphing skills. I hope that you've learned about graphical relationships, about how to make a graph, and how to determine slope of your graph, and what the area underneath of a line represents.